Good morning, Year 10. This is Ms. Teresa. Today we're going to discuss problems regarding refractive index, critical angle, and total internal reflection. Our lesson objective for today is to solve problems about refractive index, critical angle, and TIR, success criteria, I can apply Snell's law, concepts of refraction, and n is equal to 1 divided by sine c in solving problems. Here are the equations we need for the problem solvings ahead. The first one is the Snell's law. N is equal to sine I divided by sine R. N is the refractive index of the material. I is the incident angle and R is the refracted angle. And the next one, N is equal to V1 divided by V2, where V1 is the speed of light in the first medium and V2 is the speed of light in the second medium. N is equal to C by V. C is the speed of light, which is 3.0 times 10 raised to the power of 8 meter per second, and V is the speed of light in the second medium that it enters into. And the last one, it's the relationship between critical angle and refractive index, which is N is equal to 1 divided by sine C. C, which is capital letter, is your critical angle, and the small letter c is the speed of light, which is 3.0 times 10 raised to the power of 8. You should not mistake these two. We should not confuse these two together, but actually this is not being used much in IGCSE. These three are being used. Okay, if you're not comfortable with N as the refractive index symbol, you can also use RI. In other problems, they use RI instead of N for refractive index, so that's okay. Whatever you choose, it will be the same thing if you're going to use the correct equations. First problem. The speed of light in air is 3.0 times 10 raised to the power of 8 meter per second. The speed of light in a transparent liquid is 2.0 times 10 raised to the power of 8 meter per second, and the angle of incidence is also given, which is 40 degrees angle of incidence. We're going to calculate for refractive index of the liquid and the angle of refraction in the liquid. So what formula are we going to use? It's easier for us to use the formula first. N is equal to V1 divided by V2, where V1 is the speed of light in air, which is 3.0 times 10 raised to the power of 8 meter per second, and divided by V2, which is 2.0 times 10 raised to the power of 8 meter per second. 2.0 times 10 raised to the power of 8 meter per second. Okay, let me just change my pen color so that we can show the difference. Okay, so in here, this is, we can cancel out meter per second and meter per second, as well as 10 raised to the power of 8 and 10 raised to the power of 8. Now we're left with 3.0 divided by 2.0, which is now equal to 1.5. Now what's the SI unit of refractive index? There will be no SI unit since we already cancelled out meter per second, and meter per second is the ratio between two numbers, so the result will be no SI unit. So that's it for the first problem, refractive index of the liquid. Now we're going to solve for the second one. The second one is the angle of refraction in the liquid. So the first one, our N, we solved 1.5. Okay, so this we have to bear in mind. The angle of refraction in the liquid, which formula are we going to use for this? It's N is equal to sine I divided by sine R. Okay, since we should solve for for R, not for I or N. N is already given. I is already given. It's 40 degrees according to this one in here. In the problem, it's 40 degrees, so we're going to solve for R. So sine R is equal to sine I divided by N. Now we're going to solve for R, not for the sine of R, so we're going to rearrange that. Then R will become the inverse sine of sine I divided by the refractive index, inverse sine. Okay, so you're going to divide sine I divided by N first before getting the inverse. So now sine I inverse sine. Sine I is sine I, which is 40 degrees, sine 40 divided by 1.5. Okay, so this is so messy. Let me rewrite. So now R, we know that the formula, and we should not forget n is equal to 1.5. We solved it earlier. So inverse sine of the angle of incidence, which is 40 degrees as given in the problem, divided by the refractive index 1.5. So if you're going to calculate, first you're going to enter in your calculator sine 40 and then get divided by 5 and then get the inverse sine of it, and the answer will be 25.4 degrees. Okay, so are you going to round it up to the whole number, to the nearest whole number? Actually, there is a range of answers that will be given in a marking scheme in these kinds of problems, so do not worry about rounding it off or getting like 2 decimal numbers after this. No, they are going to give you a range of answer from, let's say, 25.4 to 25.5, so don't worry about that. Okay, so that's for the first problem. Next problem. Figure 6.1 shows a ray of light incident on a glass block at A. This is A. The critical angle of the glass is 41 degrees, so C is equal to 41 degrees. Okay, the critical angle, okay, 41 degrees. Calculate the refractive index of the glass. Now we have critical angle, therefore automatically we are going to use the equation n is equal to 1 divided by sine of the critical angle. If you're not comfortable, I'm telling you again, of n, then use Ri. So we are going to look for critical refractive index, not critical angle. Therefore, this is just a simple what's this, substitution. So n now is equal to 1 divided by sine of the critical angle, which is 41 degrees. So if you are going to enter that in your calculator, 1 divided by sine 41, so n here is equal to 1.52. okay, so that's the final answer, and that's for problem number 2, the second one. So this is 2 marks. Moving on to the next problem. For blue light, the refractive index of a particular type of transparent plastic is 1.5. Calculate the critical angle for blue light in this type of plastic. So we already know, we're very familiar that n is equal to 1 by sine c. Okay, this is the relationship between critical angle and refractive index. But now we're going to solve for critical angle instead of n. So we are going to rearrange our equation this way. So now sine of the critical angle is equal to 1 divided by n. And then since we're not going to find for sine c, we're going to find for c itself, the critical angle. So we're going to rearrange further. Sine, inverse sine now of 1 divided by n. Now you have to divide 1 divided by the critical angle, the refractive index first before getting the inverse sine. So substituting, we're going to substitute now. C is equal to inverse sine of 1 divided by the critical angle is, the refractive index is 1.5. If you enter that in your calculator, finally we'll be able to get 41.8 degrees. So that's the final answer. Are you going to round it off? Now there's a range again of answers that will be given, so do not worry about that. If you want, then you can round it off to 42 degrees, which is still fine. Okay, so that's all for this problem. Moving on to the next problem. For blue light, the refractive index of a particular type of transparent plastic is 1.5. So that's the refractive index. And a block is made of this type of plastic. Blue light traveling in a vacuum is incident on the side of the block at point P. So this is only blue light. So it means that there's only one color Therefore, if it's only made of one color of light, we call it monochromatic. Okay, single color of light. Now, figure 8.1 shows that the angle of incidence, angle I, is 45 degrees. Angle I is equal to 45 degrees. Now, first one, calculate the angle of refraction, R, of the light in the block. So we are going to use the formula N is equal to sine I divided by sine R. But since we're going to solve for R only, so rearranging, sine R is equal to sine I divided by N. Now, we are going to solve for R only, therefore we're going to get the inverse sine of sine I divided by N. Okay, let me just clear that up. Okay, so now our formula to be used is R is equal to inverse sine of sine I, which is 45 degrees incident ray, divided by 1.5 as given earlier on the upper part of the problem, and I cannot see it anymore, so this is the equation. Now divide this first, sine 45 divided by 1.5, because before getting the inverse sine, and finally we'll get the answer 28.13 degrees. Okay, now since we're going to draw on the second part of the problem, we're going to draw, so it's safe for us to round it off to 28 degrees. Okay, so you are going to draw it, use your protractors. You're going to draw it here, and you're going to measure it from the normal, not from here. It should be from this side, the normal. Okay, so this should be 28 degrees if you're going to draw it in your notebooks. So the angle of refraction is 28.13 degrees, rounded off to 28 degrees, and you're going to draw it later on. Okay, that's it for this problem. Next problem, figure 6.1 shows light passing from air into the glass block. So this is the figure. Using information from figure 6.1, calculate the refractive index of light in this type of glass and the critical angle. So now a less careful student will use immediately 29 degrees as the angle of incidence. Please do not make that mistake. You have to calculate first for the angle of incidence, 90 minus 29 degrees, so you'll get 61 degrees as your angle of incidence. Please be careful with your figures also. Now we're going to calculate first for refractive index. Therefore, refractive index using angles, N is equal to sine I, which is 61 degrees, divided by sine R. Now we can safely use 33 because it's actually the refracted angle. So sine of 33 degrees. Now calculating that using our calculators, we are going to get 1.61 as your angle of refractive index. This is our refractive index. So let's just note for that, N is equal to 1.61. We're going to note for that because we're going to use it for the second part of the problem, which is solving for the critical angle for light traveling in this type of class. So N in this case is equal to 1 divided by sine C. Again, we're going to use the equation C is equal to inverse sine of 1 divided by the refractive index, which is 1.61. So this one you have to divide first before getting the inverse sine. So finally you'll be able to calculate for critical angle as 38.39 degrees. Okay, don't be worried about rounding it off or getting the three significant figures. Usually they want three significant figures here, so 38.4 is fine, and they are going to give you a range of values. And don't worry, the range of value, as long as your C is correct, then this range of value will your answer for critical angle will also be considered. Okay, that's it for this problem. Okay, next. Figure 6.1 shows a protractor superimposed on the path of a ray of light. The light traveling in a glass towards the boundary with air. Okay, so this is your figure. Now this will just test your ability in reading and measurements and so on. So this is easy, but you have to be careful. Do not calculate the angle of incidence from the horizontal. You have to always calculate it from normal over here. So if you're going to calculate for that, this is 10, 20, 30, and it's pointing there at 5. Therefore, the angle of incidence is 35 degrees. This is easy, but most students, they are calculating for this angle. This is wrong. They should calculate for this angle. They should read for this angle, this part. Okay, be careful from the normal all the time. Okay, this problem is actually connected to the first one, the previous slide. So the angle of incidence that we calculated there is equal to 35 degrees. We're just going to note it over here so that you will not forget. The refractive index of the glass in here is 1.56. Calculate the angle of refraction in the air. So angle I is 35 degrees. Now we're going to solve for R. Sine R is equal to sine I divided by N. Sine I divided by N. Now, as we know already that we have to get the inverse sine of everything. So sine -1 divide into sine of 35 degrees, as we have read earlier, divided by N. It's given here, it's 1.56. 1.56. So calculate that. We're going to get an angle of refraction which is equal to 21.57 degrees. Okay, if I'm wrong, please correct me. You can just reach me over there. Now state what is meant by the critical angle. So this is related to our lesson yesterday, and critical angle is an angle at which produces an angle of refraction of 90 degrees from the normal. So if we will draw something like this, and we have normal over here, and the light ray will originate from the denser medium to the less dense to the rarer medium, then your angle of refraction will look like this. Okay, so that's your critical angle, but you have to define it in words, not in figure. So that's it. And now finally we're going to calculate for the critical angle. This one, critical angle. The refractive index is 1.56, and we already know the angle R, which is 21.57. But do we need that? No, actually we don't need for a critical angle. So critical angle is equal to inverse sine of 1 divided by 1.56. So if you're going to solve for that, C now will be 39.87 degrees, or 39.9 degrees. Okay, so that's it for this problem. So we're just going to summarize. For the angle of refraction, we got earlier 21.57 degrees, and critical angle is the angle at which produces an angle of refraction of 90 degrees. You have to write that down. And then finally we have here 39.87 degrees as your critical angle. So correct me if I'm wrong. I'm just there in our private chat. You can chat with me anytime. Okay, so that's it for this problem. Next, this is actually your work. Okay, there's the two problems, they are related to each other. Your work will consist of this slide and the next slide after that. It is actually it will summarize all the things that we have learned about refractive index, critical angle, and total internal reflection. Total internal reflection problems, I will give you more on that tomorrow so that we can apply our knowledge about it. So what have we learned today? We applied Snell's law. and we also applied the concepts of refraction, and we used n is equal to 1 divided by sine c in solving problems. We also used n is equal to sine I divided by sine r, and n is equal to v1 divided by v2 as well. Now if you're not comfortable again of using n as your refractive index symbol, you can also use ri, no problem. I hope you enjoyed the lesson for today. This is Mr. Essa signing off. As always, have a nice day.